All right, section 1.3. Section 1.1 and 1.2 was probably stuff you mostly knew already. But I think section 1.3 might be kind of new. In section 1.3, we're going to deal with approximate numbers. And this is a really, really important topic in science. When we measure things, we are approximating. And by measure, I don't necessarily mean just taking a ruler and measuring something, but that's approximate too. So, for example, if I tell you I'm 5 feet 11 tall, 5 feet 11 inches, I'm not exactly 5 feet 11. I might be somewhere between 5'10 and a half and 5'11 and a half. This morning I stepped on the scale and it told me I weigh 206 pounds. Again, I don't weigh exactly 206 pounds. That's an approximate number. If I told you my temperature was 98.4 degrees, again, that's an approximation. It's a little bit better than the first two examples I gave because it's accurate to one decimal place, but still approximation. So, just like we have the order of operations, which tells us how to add, subtract, multiply, divide, so that we're all doing it the same way, so we all get the same answer, we have rules about dealing with approximate numbers. How do you add, subtract, multiply, divide, so that we all get the same answer? And that's what we're going to look at in section 1.3. Now, before we can do that, we have to talk about significant digits. Significant digits is what the phrase implies. It's the digits in a number that matter. And that seems a little weird. Some matter and some don't, but that's what we're going to talk about. As you can see, kind of a long list of rules. Basically, there's two things here. What if your digit is not 0? And then all the other rules are what if it is 0? So 0 is the hard one here. So all non-zero digits are significant. So if I give you the number 352, all those things are not 0, 3, 5, and 2. So we would say this has 3 significant digits. And I'm going to abbreviate significant digits as SIGDIG. Takes a lot less time to write. Or if I gave you 14.837, again, none of those things is a 0, so there's 1, 2, 3, 4, 5 significant digits. All right, now let's talk about all the 0 rules. All zeros that occur between any two non-zero significant digits are significant. All right, so that would be something like 4,208. This 0 is in between two significant digits, so now it's significant. So there's 1, 2, 3, 4 significant digits. Or let's say I gave you 11.0013. Again, these zeros are trapped between significant digits, basically trapped between things that aren't 0. So they are significant. 1, 2, 3, 4, 5, 6. 6 significant digits. All right. All zeros that are on the right of a decimal place and also to the left of a non-zero digit is never significant. All right, that sounds confusing. It's not. It's this. 0.0052. These zeros are on the right of a decimal place and also left of a non-zero digit. These don't count. So these two zeros are not significant. Only numbers that are significant are these two. So this one has two significant figures, sometimes called significant figures. I chose to write fig this time. I don't know why, I just did. Okay? So basically, the way I think of this is these zeros, really all they're doing is holding position to push the 5 into the right spot. They don't count. These zeros are just placeholders. They're not significant. They don't count. Compare that to all zeros that are on the right of a decimal point are significant only if a non-zero digit does not follow them. Okay, so what I mean by that is I wrote two numbers here. 20.00. These zeros are right of the decimal place, and there's no non-zero number behind them, so these are significant, which makes this one significant because now this 0 is trapped between two significant digits. So trailing zeros like this are significant. Zeros like this that are only there to push the number into the right position are not significant. So basically what's happening here, think of this is two significant digits, two decimal places. Think of money. You had a jar full of money and you added it up and it turned out to be exactly $20. So these zeros are significant because they're telling us that it's not $20.03. We're kind of no longer saying this is an approximate number. This is exactly $20. Although it could be approximate still if we're dealing with some sort of instrument that reads to 3 decimal places. All right, anyway, this 20 has 4 sig figs. Where this number only has 1, because these zeros, they are right at the decimal place, but they have a non-zero number behind them. So this number only has 1 sig fig, 1 significant digit. All right, so notice the difference there. Trailing zeros are significant, zeros in front are not. Unless there was a different number here. If there had been an 8 here, then all these zeros would be trapped in between and they'd fall into this rule. All right, all zeros that are on the right of the last non-zero digit after the decimal point are significant. So that's saying something like 4.200. These zeros are not placeholders. They're not forcing us to put the 2 in the right decimal place. They're not placeholders. What they're telling us is the instrument we're using is accurate to 3 decimal places. So these zeros are significant in that the instrument we were using gave us that number. Okay, so this one would have 4 significant digits. All right, got one more of these. How about 0.0052000? All right, so again, 0 is a confusing number when we're talking about significant digits. These 2 zeros are only placeholders. They're there to push the 5 into the right spot, push it into the thousands position. Yet these zeros here are telling us we're dealing with an extremely accurate instrument that's accurate all the way to this many decimal places. Which tells me these 2 zeros are not significant, these 3 zeros are. They're not placeholders, they're telling me the accuracy of my instrument. So this one has 5 significant digits. All right, the last rule. Trailing zeros left of the decimal place are not significant unless they come from measurement. All right, so what I mean there, let's say I gave you the number 2,500. In general, the vast majority of the time, we would say this has 2 significant digits. Trailing zeros on a number like this are not significant. Trailing numbers on a decimal are significant. Notice the difference. These are left of the decimal place. Now, what I mean by unless it comes from measurement would be, let's say we were counting a bunch of $10 bills. Then my instrument, $10, is accurate to this place. So if I want to indicate that my machine, or however I'm getting this number, is accurate to that position, I would put an underline under it to indicate that digit is now significant. Normally it would not be, but now I'm dealing with $10 bills and I'm telling you I came up with exactly this much money, so that 0 is significant, so this one would have 3 significant digits. Okay, so once we know about significant digits, we can start talking about how do we add, subtract, multiply, divide, do roots. All right, so we have 2 definitions. Accuracy. The accuracy of a number is the number of significant digits it has. So, for example, this number back up here, we would say has 5 significant digits. So its accuracy is 5 significant digits. The precision of a number is the decimal position of the last significant figure. So going back up to this number here, 14.837. We would say it has 5 significant digits, so its accuracy is 5, but its precision is that position right there, which is the thousandth, I have trouble saying that word, thousandth position. Okay, this number, 3 significant digits, accuracy is 3. Precision would be the ones place. It's only accurate to the nearest one. All right, so these play a big part in how we add, subtract, multiply, divide. Rules for operations. For multiplication, division, and exponents and roots, so all those things, round the answer to the same number of significant digits, the accuracy, as the number in the problem. If the numbers in the problem have a different number of significant digits, use the lowest. All right, so let me give you a quick example. If I gave you 18.2 and told you to multiply it by 5.7, we grab our calculator, because I don't want to do it by hand. Not that I couldn't, but pain in the neck, right? Try to get this in a position where it looks good. 18.2 times 5.7. I don't write that answer down. That's not the right answer. Because we had to count the accuracy of each number. This one has 3 significant digits. This one has 2 significant digits. So I have to round off to 2 significant digits. Oh, sorry about what's happening on my screen here. Some things I just can't turn off and they pop up on me. All right, anyway, so 3 significant digits, 2 significant digits. I can only give you an answer to 2 significant digits. So I have to call it, 2 significant digits would be these 2. So I have to call this answer 100. And I have to indicate that that number right there is significant. So I underline it. All right, let's do one more of these. 14.036 times 9.14. Again, I grab my calculator. 14. Position the calculator so you can see it. 14.036 times 9.14. Not the answer I write. This one has 1, 2, 3, 4, 5 significant digits. This one has 1, 2, 3. So I have to give my answer to 3 significant digits, which means my answer is 128. All right, we're close to time limit for this video, so we'll finish up this section in a second video.